Hello, everyone. In this talk, I will introduce our new true random number generator, a multimode ring oscillator-based TRNG for the FPGAs. Yeah. So my slides are not moving. Okay, now. Okay, so let's get started. First, I will go through description of a modern approach to design of TRNGs. You saw this many times, I would say, but it's nice to recapitulate a bit. And I will introduce our design, the three-edge ring oscillator true random number generator with time-to-digital converter. I'll present its security analysis. Then I'll explain how we apply the post-processing based on the generator matrix of a linear code to improve its throughput. And then I will give comparison of performance with some other work. This figure shows a generic architecture of a modern TRNG. The digital noise source is the core of a TRNG design, as it is the only component in the whole architecture with the non-deterministic behavior. All true randomness is generated by the entropy source and often in the form of analog signals. Then we have the digitization module, which is needed to convert these analog signals into a digital form. The combination of the entropy source and digitization module forms a digital noise source. The produced outputs of the digital noise source are called the raw random numbers. The raw random numbers should be available for inaccessibility by the so-called total failure tests. And these tests are implemented for fast detection of the total breakdown of the entropy source. Unfortunately, the raw random numbers are subject to statistical defects, for example, bias and autocorrelation between output bits. Therefore, we have a post-processing or conditioning module, which is applied to these non-ideal raw random numbers to improve their statistical and security characteristics. So this module basically extracts and densifies the randomness of the raw random numbers. And post-process numbers are called internal random numbers. Another important part of every TRNG designs is online tests, or a set of online tests, also known as embedded tests, which are used to detect failures generating raw random numbers. What is very important is that modern TRNG design has to be supported by stochastic model. Why? Well, because security is guaranteed by two requirements. One is good statistical properties. However, this is not enough. Output bits should also be unpredictable. The good statistical properties are verified by statistical tests, while unpredictability is much harder to assess. In cryptographically secure pseudo-random number generators, this unpredictability is guaranteed by the underlying approved crypto algorithm, AES, for example, or catch. However, in true random number generators, the unpredictability is guaranteed by sufficient entropy rate, an approved design approach supported by the stochastic model. Thus, the stochastic model enables quantification of the lower bound on the entropy or unpredictability of the raw and internal random numbers. Now, due to their importance in hardware security, the TRNGs have become subject to evaluations by US, European, and Chinese certification bodies. The TRNG design, as I said, should provide theoretical justification of the unpredictability of its output. However, this is not always required to be a stochastic model, but just a description is enough for American standard NIST SP 890P, which is from 2018. However, TRNGs that are compliant with European standard, that is German AES 31, should also have a stochastic model. One difference between these two approaches is that the AES 31 requires defining a lower bound of the Shannon entropy, or estimating it to be precise, while the NIST requires estimating the mean entropy. Also, AES-31 puts strict requirements in the quality of the random numbers generated by the TRNG, while NIST does not put such a requirement. However, NIST requires that if the post-processing which is used is not cryptographic, then the mean entropy has to be at most 0.99 bits of mean entropy. So we have these two very similar approaches, but they have requirements that are sometimes confronting with each other. Thus, when designing our new TRNG, our goal will be to have at least 0.999 bits of mean entropy for the internal, that is post-processed random bits, to be sure to satisfy both AES-31 and NIST standards. Our goal is also to have a realistic stochastic model that will account for the effects of inherent hardware process variations and employ it to actually estimate the lower bound of mean entropy contained in each random bit. Our goal is also to have a high throughput and low area with also low design effort. And here in the design effort, we think of manually placing and routing circuit components instead of just using hard description language like variable VHDL. And to obtain a good area, versus throughput trade-off, we need to optimize both digital noise source and post-processing. In that way, we will obtain the best efficiency trade-off. So we start by introducing the architecture of the digital noise source of our TRNG. And why is our TRNG called TRO-TDC TRNG? Well, because it is based, as I said, on 3-edge ring oscillator with time to digital conversion. And this is how it looks. The entropy source of this TRNG is a 3-edge mode ring oscillator, which consists of 3 inverting and 3 non-inverting stages. These stages, 3 stages, at the same time inject 3 inverting stages at the same time inject the edge in the ring oscillator when the enable signal run is set to 1. The edges, these 3 edges will have identical mean period since they propagate through basically same stages. Thus, the frequency of the resulting ring oscillator signal at the output of any of the 6 stages will be 3 times higher than the frequency of a single edge ring oscillator with the same number of stages. Now, to efficiently exploit the independent timing jitter in each edge in the ring oscillator, we use one time-to-digital converter as a digitization. This time-to-digital converter consists of a delay line formed by small multiplexers called bins and falling edge D flip-flops. Those structures are available on most FPGAs of 2 biggest vendors, Xilinx and Intel. So the output of these small multiplexers, which are called bins, are connected to the D inputs of the flip-flops. Now, the propagation delay, it is very important to note that the propagation delays of these multiplexers are much smaller than the propagation delays of the individual stages of the ring oscillator. And how is the entropy source and a TDC, how are the entropy source and the TDC connected? Well, as shown here, the signal from the 3rd non-inverting stage F, is connected to input 1 of the first multiplexer of the delay line, whose select signal comes from the 2nd inverted stage C. So the signal from stage C is also used as a clock signal for the D flip-flops of the TDC. Then we have a pulse width encoder, which is a combinatorial circuit that outputs a raw bit and a raw bit valid signal based on the values of the D flip-flops. So the raw bit that is going to be output depends on the parity of the number of 0 values relative to the total number of D flip-flops in the TDC. the raw bit valid signal is going to be set only when the first and the last bit flip-flop in the TDC, sorry, have value 1. And there is at least one D flip-flop with value 0. Okay, let's see how this configuration actually enables us to capture the timing jitter effects of all 3 edges with this timing diagram. So first, the ring oscillator is enabled for a period of time at TACC, which is also called accumulation time, by setting the signal run to 1. This accumulation time is selected so that all 3 edges accumulate enough timing jitter during that time period. The propagation, as I said, of the state of the signal at the output of stage F, the delay line is enabled at the rising edge of the signal at the output of stage C. Since the signal at the output of stages C and F are approximately 90 degrees phase difference, as you see on this diagram, the signal at the output of stage F will be low, and the instant delay line will start transitioning from 1, which value that they had previously, to 0, as shown in this figure. Now, when the rising edge at the output of stage F occurs, the bins in the delay line that were previously set to 0 will start transitioning to 1. So the delay line basically now reflects the state of the signal at the output of stage F. And finally, at the next falling edge at the output of stage C, the corresponding D flip-flops will sample the state of the delay line. And in this manner, the effects of all 3 edges will be captured in the D flip-flops. The sample value of D flip-flops is then transferred to the pulse width encoder to be encoded to 1 raw bit. After that, the ring oscillator is disabled for 1 clock cycle to reset it. During that time, the raw bit value and its validity signal are evaluated by the pulse width encoder so that they have stable values on the following rising edge of the clock signal when they are transferred to the system clock delay by those 2 D flip-flops at the output at the number. Note, however, that the rising and falling edges who participate in this process can originate from any end stage, so they can be whatever edge in the ring oscillator. That's why we denote them. We use alpha to denote the last rising edge, and gamma the last falling edge at the output of stage C, and we use beta to denote the last rising edge at the output of stage F, in order to avoid confusion of using always these triples 2, 0, 1, or 1, 2, 0, or 0, 1, 2. Okay. Now, as I said previously, these unavoidable variations of the propagation rates of the pins in the delay line will influence the amount of the entropy that we can extract with this TRNG. So to improve the uniformity and to suppress the bubbles that appear in the delay line, that is when the delay of one stage is appears basically before the delay of another. We decided to combine 2 adjacent physical bins, so basically 2 multiplexers in 1 bin of the delay line. We also, as you see here, have a 9-bit ripple counter, which is connected to the output of stage C and increases on the rising edge. And its role is actually twofold. It's used in design phase to estimate the amount of jitter accumulated by the 3 edges, as well as their oscillation periods, and it also serves as a total failure test. So as a total failure test, the counter is used to monitor the number of full oscillations during the accumulation time. And if the edges collide before the raw random bit is generated, due to attack or some environmental influences, this counter will have much lower values than during the regular operation. Now, as I said, due to noise influences, even if there is no adversarial noise, even if there is just white Gaussian jitter noise, the 3 edges will inevitably collide. And they will compel the ring oscillator to a single edge. To inspect this, we monitor the evolution of the ring oscillator with the increase of the measurement time, as it's shown in this figure. So we performed the measurements in the steps of the period of the system clock, and for each time step, basically we repeat the experiment 100,000 times. So we observed that for the periods under 56 nanoseconds, and above 232 nanoseconds, we can either not reliably detect the period of the ring oscillator, or the ring oscillator exits the triage mode. So in the beginning, due to big quantization noise, the measurement error will be high, as it's seen in these steps in the beginning, and at the end, the period will start to increase, signaling that the edges start to collide, so we no longer have 3 edges in our ring oscillator. For the implementation of this design on Xilinx Zinc FPGA, we calculated that the period of the 3-edge mode is around 1043 microseconds. Now, I'll present only a sketch of the security analysis of this design. So what is security analysis? Well, it provides analytical assurance for the quality of the random bits. We needed to estimate the lower bound of the min-entropy of the raw random bits by using the stochastic model. To start with, we have to make some baseline assumptions about their both entropy source and the digitization. So our baseline assumptions are that there is some amount of independent white Gaussian noise in the source, in the design, that the raw bits are independent. This is due to the reset between the successive raw random bits. Then we assume that the bin delays are non-uniform, that is, we need to characterize them precisely. And we assume that the other noise sources are present, but they will not be exposed in our design. Now, to keep, again, things relatively simple, I will only discuss the digitization element. So, as you remember from 3 slides ago, the time-to-digital converter and the pulse width encoder map a relative position of the edges alpha and beta to the edge gamma into a random bit. So, at the sampling moment determined by the edge gamma, the bins in the relay line should contain a string of at least 1 bit with value 0, encircled by the bins with strings of 1s, as you see in this picture. So the number of bins with value 0 in the relay line is referred to as pulse width. This pulse width can have any value between 1 and n-2 bins, where n is the number of total bins in the TDC. So for odd pulse width values, this encoder will output 1, and for even it will output 0. Therefore, we need to calculate the probabilities of all possible values of the pulse width. Now, for a given position of the edge gamma, that is x in this figure, we first have to calculate the probability that the pulse resulting position in bin j will have a width of I bins, as depicted also in this figure. So this probability is given by this first expression at the top of the slide. Here we multiply the probability that the edge beta will be in bin j, and the probability that edge alpha will be in bin j plus 1. Now, to remove the condition on the starting position bin, we sum over all possible starting positions j and obtain this second equation. Then, the condition to the position of the edge gamma can also be removed by integrating over all possible values of gamma. Remember that gamma is, based on our assumption, has a Gaussian distribution, as well as alpha and beta, and they are all 3 independent. Now, since the pulse width encoding is only used when the pulse is captured in the time-to-digital converter, we need to calculate the probability of a pulse width being I, given that the pulse of any width has been registered in the TDC. And finally, the binary probabilities, that is the probabilities of the raw random bit being 1 or 0, are computed by summing the probabilities of all odd pulse widths for bit 1 and all even pulse widths for bit 0. And this is given by the last expression. Note that to precisely determine these probabilities, we have to know the variances and means of all 3 edges, as well as the propagation delays of individual bits. The min-entropy because of our independence assumption, can be directly calculated from these binary probabilities. So at the end of our security analysis, we got the mean entropy. We got the expression for the mean entropy. Okay, now we have a stochastic model, we have our TRNG design, we implement our design on FPGA, and we calculate the so-called platform-specific parameters. So we can calculate the mean entropy estimation by using the formula in the previous slide. First, platform-specific parameter of importance is the jitter strength. The jitter strength characterizes the increase of the Gaussian jitter variance with time. For our platform, having Zinc FPGA, we calculated the jitter strength to be around 9.7 femtoseconds. Now, by observing the variances of edges alpha and beta and gamma, we can see that due to the fact that edge alpha occurs always before beta and beta occurs always before gamma, so this should be gamma not x in this slide, sorry, that variance of alpha is the smallest out of 3. So to simplify our model, we say that all 3 variances will be equal, and they will be equal to the variance of the edge alpha. Now, to calculate this variance, or the lower bound of this variance, we need to use another platform-specific parameter, and that is the period of the ring oscillator, which we saw several slides ago. That is around 1043 picoseconds. Now, by using that counter at the output of the stage C, and the fact that we know the mean period of the edges, we can calculate the lower bound on the variance of alpha after accumulation time PACC by this expression here. Finally, the last thing that we need is to determine the propagation delays of the individual rings in the TDC. They're depicted in the figure on the right. Now, what is interesting here to note is that there are big discrepancies between the individual delays and between the falling edge and the rising edge propagation delays. So falling edges are upper half, and the rising edges are in the bottom half. So this factor will influence our entropy estimation. Finally, we set the system clock frequency to 125 megahertz. That means that system clock period is 18 nanoseconds. Now, using the stochastic model and measured platform parameters, we can numerically calculate the mean entropy estimation of the raw random bits for any time difference between means of edges alpha, beta, and gamma, and for different amounts of accumulated jitter. Note that these means, mu alpha, mu beta, and mu gamma, cannot be precisely determined at the design time, and their values might also change during the operation due to the influence of other not exploited and possibly arbitrary sources. So the lower bound of the mean entropy is obtained by finding the global minimum for each value of the given jitter. Figure on the left shows the mean entropy estimation as a function of the time distances of mu alpha and mu beta to mu gamma for the standard deviation of jitter of 16.52 seconds. The global minimum is marked by the black dot. What we can observe is that TDC, as I said, the TDC's non-uniformity will significantly impact the estimated mean entropy, as we see that our graph, although mainly colored in red, that means it has high entropy, there are a lot of wells of blue color, basically, which mean that we have significant drops due to linearities in the mean entropy. What we are also interested is the dependence of this minimum of the mean entropy on the amount of accumulated jitter, so on sigma, or equivalent of the accumulation time. So the dependence of sigma is depicted on the lower axis, and the dependence on accumulation time on the upper axis. But the accumulation times are in the steps of the system clock period. What we see here in the red line is a rapid increase of the mean entropy up to the accumulation time of around 40 nanoseconds. Then for the longer accumulation times, this growth kind of tapers off since the TDC's non-uniformity cannot be overcome even with this high jitter. Then, to confirm the validity of our estimations, we applied the entropy estimators from the NIST SP890B test suite on the raw random bits obtained by this design for different accumulation times. We also see that our estimations are always lower than those of the NIST test suite. However, our mean entropy is very slowly approaching to the desired bound of the 0.99999 bits of mean entropy, and the edges become very likely to collide before enough entropy is accumulated. So, to increase the mean entropy while maintaining at the same time high throughput with relatively low implementation cost, we use the post-processing based on the binary linear codes. The principle of this post-processing is rather straightforward, as it involves only matrix vector multiplication. That is, we have G, which is a k times n generator matrix of a binary linear nkd code, where n is its length, k its dimension, and d is its distance, so standard notation. This matrix multiplies vector x, which is vector of n raw random independent bits, which we obtain from the digital morphers, and as a result, we obtain a vector y, which is vector of k post-process bits with a high enough entropy rate. The entropy rate of y is given by this formula. Naturally, this post-processing induces the loss of throughput by a factor of k over n, that is the rate of the code. So, to optimize the throughput of the TRO-TDC TRNG, we need to properly select the generator matrix of the linear code such that the mean entropy of the post-process bit is higher than 0.999 and also achieves the highest possible throughput. Thus, this selection depends on the existence of the linear code with needed dimension k, as calculated by this formula, and minimum distance d, as well as the rate of the code k over n, because we also want low influence on the throughput. So we start a list of around 33,000, basically a best known binary linear codes, and construct a sorted list of suitable codes. First, for each code, we determine the minimum necessary mean entropy of the raw bits, which is needed to achieve the mean entropy higher than 0.999 and the code rate k over n. Then we classify a code as suitable if, among all codes with the same rate, it has the lowest required minimum necessary mean entropy of the raw bits. Among all codes with the same minimum necessary mean entropy of the raw bits, it has the highest throughput. And all other suitable codes with higher rates have higher minimum necessary mean entropy of the raw bits. So when we prune this list, we are left with 468 suitable codes. This list is then sorted in descending order of the minimum necessary mean entropy of the raw bits. Then, for different accumulation time, we calculate the lower bound of on the mean entropy of the raw bits, and from the list of suitable codes, select the first one with lower minimum necessary mean entropy of the raw bits. This figure shows maximum achievable throughput for different accumulation times. You can see that the highest throughput is around 12.9 megabits per second, and is achieved for the accumulation time of 24 nanoseconds. For this, we use a generator matrix of 411712 codes. The second highest throughput, however, is a throughput of 12.5 megabits per second, so a bit lower, which is achieved with the generator matrix of 24128 code. Now, to demonstrate the advantage, basically, of the linear code generator matrix post-processing, we also showed here the throughput that can be achieved with end-stage XOR post-processing. And in end-stage XOR post-processing, the post-process bit is a parity of the sum of n consecutive non-overlapping random bits. Then for each value of the accumulation time, we first calculated the minimum number of stages needed so that the mean entropy of the post-process bit is higher than 0.999, and then the corresponding throughput. In this figure, as I said, we can also observe that the throughput of the end-stage XOR post-processing is always significantly lower than the throughput after post-processing with the generated matrix of a linear code, which can be seen as the difference between the red and blue lines. Now, the 411712 code is neither cyclic, is not cyclic, sorry, and it does not have a generated polynomial that can be used for efficient hardware implementation, because we know how to do that. However, we observe that if we somehow sacrifice throughput, an efficient hardware implementation can be achieved. We do this by using the generator matrix of the 2412-8 code, which is given on this slide. Here, I12 is the identity matrix of size 12. This matrix has a 12 times 12 circle and submatrix where all of those are circularly shifted. And this representation exactly enables a very compact implementation, as shown here. So the implementation of post-processing consists of 12 bit flip-flops, 5-bit counter, 2 output D flip-flops, and several XOR gates. So how it works: during the first 12 clock cycles, the raw random bits are shifted into the D flip-flops Q0 to Q11, and the valid signal is set to 0. And then in the next 12 cycles, these registers are connected in a circular shift register through multiplexer, the input of the first D flip-flop. And the valid signal is then set to 1. At the same time, the post-process bits are obtained by XORing the incoming raw bits and the outputs of the circular shift register at these positions, which are determined by the ones in the first row of the matrix A. So this of the matrix on this slide. Okay, comparison. As many of you know, fair comparison is always hard. That's also true for TRNG designs and FPGAs. Mostly because the older designs do not have stochastic model and an explicit statement of the amount of entropy per bit that this TRNG produces. Further, some TRNGs that do have entropy estimation do not always use the same metric or the same goal of the entropy of the post-process bits. So in this comparison, we restrict only to designs for designing FPGAs which have stochastic model and the entropy estimation. So for each design, we reported here hardware validation, throughput, and design efforts. So certain designs require manual placement and routing, while the others require only relative placement constraints. And some designs do not require any constraints at all, so they have the lowest design effort, which is required. Now, when we compared our design with the TRNGs, with the TRNG with the throughput, which is of around same order, that is DC TRNG, our design is much more lightweight. So 67 versus 33 slices. On the other hand, if we compare our design with the TRNGs that have lower hardware resource consumption, like Aero, COSIC, PLL, TERO, our design achieves several orders of magnitude higher throughput without the need for manual routing. And to conclude, we show the design of a highly efficient digital noise source, which achieves good trade-off between the area and the throughput, randomness throughput. It has relatively low design effort. We don't require any manual routing. And it is compatible with both AS31 and NIST SP890P approaches. With this, I would like to end my talk. Thank you for your attention. I'll answer any questions.
Thanks, Milos. Do we have questions? Okay, I'll start. I have one. On your last slide, you have throughput as one of the, let's say, important figures of merit. And I wonder how much that is actually really important to have a TRNG that has a high throughput? Isn't it more realistic to say a TRNG should be able to produce a small amount of bits quickly, but it's not going to, it doesn't need to produce them permanently all the time, continuously? Right? It's often you want to quickly have a couple of bits to seed something, but then for a long period you don't need any bits.
Yeah, that's true. Yeah, indeed. That depends. That depends on the application. So, for example, the TRNGs are often used in conjunction with PRNGs. So you use TRNGs to seed your PRNG, which you will then use for a certain amount of cycles, and then you will receive them again. What we saw, recently by Lawrence Walker Chess last year, is that it turns out that reseeding of PRNGs might be needed much sooner than we expected. And if you have one PRNG for your mass, one PRNG for your keys, and so on, that grows very, very fast. The number of bits of TRNG that you need to receive all these TRNGs.
I was just wondering whether it would make sense to I don't know, to think of a special architecture where you say, I combine a very slow or very low throughput TRNG with a little cache memory, that you say, I take my time to produce, 200 bits, but then I have them in a fast cache memory accessible. So, when they are needed, they can be pulled out basically instantly. And then again, I have some time to refill my buffer.
Benedict, I would think the other way around. Why do people use pseudo-random number generators? Is because it's very tough to generate true random numbers at a high throughput. So that's why people go to the pseudo ones. But the architecture here, you can get high throughput with the correct amount of post-processing, so high quality, with high entropy. Yeah. So you could go for extremely lightweight post-processing or lightweight post-processing if you need after that. But it might be cheaper.
You mean you could live without a PRNG afterwards and just use the raw random numbers? Yes. Yeah, that's the other approach.
Sorry, there is work going on here. Especially if you don't, especially if you need compactness.
Yeah. So I don't know. I didn't look too much at the area, to be honest, because I was just I was impressed by this big range of throughputs. Right, we have a couple of orders of magnitude here on the slide. Or actually many, from 0.0042 up to 100 megabit per second. Oh, yeah. So I was just wondering, because I hear very often a requirement that people say, we need a lot of throughput, and actually it's not exactly what I just said, but what people often need is low latency. Yeah, for example, in an embedded device, you may need to generate some keys before you boot. And so this has to happen at very early boot stages. And essentially, the longer you have to wait for the random numbers, the longer the boot process becomes, right? And users don't like to wait. And then people come and from this formulate the requirement that they need a high throughput. But actually, they just need very few bits, but quickly, right? So that's not exactly what I just said before, 2 minutes ago. But I think it's a requirement that can be addressed maybe in a way different from just providing high throughput, right? Because if you just say, I just need to be able to produce 100 bits with low latency, and then I don't care, then I can wait for a couple of seconds for the next batch, right? That's different from asking for permanently high throughput. Do you know any work in that direction?
I'm thinking. No, I'm not sure.
Okay.
Low latency.
Then I would go for a compact one. They all have startup phases. A compact one without too much processing. So you look at the table, which one is small and compact. and does not require manual place and manual route. So the design effort is very important. You want designs that are portable and don't need too much effort when you port from one FPGA to another one. And that's this last effort.
I think so. The number that I'm looking for is like how much time passes before the first bits become available. Right, there's some kind of setup time or something. But I mean, these throughput numbers, I guess they express the throughput once everything is up and running, right? But initially the TRNG needs to kind of accumulate some. Like when you power it on, it's not going to spit out bits immediately, right? It has to accumulate some entropy and then do all of that.
But this accumulation time is the same between every random bit that you output. You need to run your, for example, ring oscillator database, not maybe my design, but all ring oscillator database. You need to let them run. Then, depending on the design, you either reset them or you let them run at the same amount of time before you generate another random bit. So you have this same amount of time that you have between the.
So the time until the first bit comes out is the same time that it takes between the 10th and the 11th bit. Okay.
In most designs, yes.
Okay, thanks. Are there other questions?
Okay. Yeah, I do have questions here.
Okay, but you wanted to add to the discussion. Go ahead.
Okay. Yeah. So for the discussion, I think if you have a compact TRNG, you can have several of them, and you can prove that they are independent from each other, or you use some isolation techniques. Then you can generate multiple bits at once, which might meet the requirement you set low latency.
Yeah. Parallelization is good. Okay. Thanks.
Okay. And hi, Milos. Thank you for your brilliant presentation and seminar. I have 3 questions. The first one is that you mentioned that you combine two delay bits together to improve the bubble problem. But after the technique, how is the bubble situation now? Is the bubble eliminated, or you still have the bubbles?
So I still the bubble is mostly eliminated, but not completely. But it's so here if you see the propagation delays, afterwards there are no zeros, for example.
Okay.
So the bubbles is So in the case that you need, if you go for the higher carry chains, if you need more, then the bubbles might still appear in the.
Then do you have some? Yeah. Then do you have some specific techniques to to filter out the small bubbles, or you only look into the period which is longer than some fixed data or fixed size?
If I look what? Sorry.
So if you still have the bubbles, but the bubbles only appears at the edge of the sample data result I'm right. If you still have the bubbles, so can you set maybe some minimal length of the period of the oscillator, so we can filter out those bubbles with some threshold there?
Yeah. So the thing is, So the thing is that I presented here, a simplified, version. So indeed, I have this a simple bubble detection in the pulse width encoder that basically detects when there is a bubble and does not output the bit. So my technique, because the bubbles appear very, very rarely, so my technique is to use this with validity. So that signal, when the bubble is detected, is not output that bit, but that bit does not occur that often, so it does not influence the throughput significantly.
So that information is discussed. Okay. And my second question is that we all know that the period jitter is highly influenced by the voltage and the temperatures. So I'm wondering, do you see the same, can you expect the similar jitter strength under different temperature or voltage?
Yeah, so the thing is that the jitter strength. So what I did is I run in parallel some other applications. So I implemented small AES, a catch-up also, to see what is going to happen. The thing is that this jitter is the jitter that is measured here is much. So I measured it in several different circumstances, and I reported the smallest number. So the thing is, this jitter is quite small. So this is around less than 10 femtoseconds. I looked into other designs that reported the jitter strength, and the jitter strength there is around 3 times bigger. So this jitter strength report here is under, I think, very conservative, because because it's 3 times lower from what is reported before, and I tested with a different operating conditions. So basically, with different stuff in around logic. Yeah, indeed. That's a good question. That's jitter strength is important.
But do you think that we can tune the voltage or change the temperature precisely to actually control the period of the sampled period in your design?
You mean the period of the ring oscillator?
In the final sampled result, because you use some techniques to sample them in a different way, then you have them lined up. You are measuring the 3 edges and the full period. So do you think that if we can control the voltage precisely, or we can control the temperature precisely, we can actually control the period?
The period of the random bits.
The sampled result. Oh.
No, I'm not sure. The thing is that
maybe I misunderstand something here. Sorry.
Yeah, the thing is with this design is that because you have, I will go back. Yeah, the thing is that because you have the state, you have all 3 edges propagating in the same stages. So if there is influence, for example, due to influence of the temperature or voltage, the delay of one stage becomes higher. It will influence equally all 3 edges, because all 3 edges propagate through the same stages. So all the influence basically that has a smaller frequency than the frequency of the edges will be filtered out, because it will influence exactly in the same manner all 3 edges. So it will not be seen.
Okay. Can you go to the next slide of the next slide? I think it's slide 10 or slide 11.
This one?
No, the next one. The one with the pulse width of PW. So yes, this one.
Yes.
The 12. Sorry. Page 12.
Maybe my slides go.
No. So you extract the raw bit by checking the parity informations of the PW.
Yes.
And how did you do that in the encoder part?
So as I said, if there is if there is a bubble in the code, which then no bit is output. So this result is only this result will only be output when there is string of zeros encircled by ones from the left and the right side. And then we XOR them all together and we obtain one number. Because as I said, the bubbles will be detected by the other.
Okay. So you XOR them together. That's a simple way. Yeah. So you know the total size of the sampled result and just check the final result. Yeah.
You know the total length, so you will know when you XOR them what the parity basically will be.
The parity of the base of the 0.
And when there is a problem, the bit will not be output.
Great. I think that's very talented way to do that. Smart way to do that. And I have one extra comment on the comparison result, on the result comparison part.
Yeah.
So if you go to that part
Right?
with the different selections of the parameters of the post-processing and the entropy.
This one.
Yes, this one, 17. Yeah.
Yes.
So with the figures, we have the accumulation time versus the throughput. But I think one thing is missing here is that it's the hardware resources consumption of the post-processing, because you use the same entropy source, but with the different post-processing techniques, you might expect different area of the post-processing. And I think those additional area might be comparable to the entropy source itself.
So indeed. Extra post-processing, as you know, will have the smallest area. So this is beyond discussion, because no matter the stage, we can implement this with the same hardware. We just set the counter on the different values. So that will be smaller always. But indeed, and that will be smaller in this implementation, of course. But the throughput is also smaller, so almost more than 2 times smaller. So I went here to find the trade-off between the throughput and the area. Yes, this consumes more area than extra post-processing, but gives 2 times more throughput. And the area of this post-processing, so post-processing with the 2412.8 code, is much smaller than the area of the digital noise source. So in comparison to the extra post-processing, it's much larger indeed, but compared with the total area of digital noise source, it's more in number of slices.
Okay, then I don't have any other questions. Thank you.
Thank you, Bokan, for your nice questions.
We have Aprilia who's raising the hand. Do you want to unmute and ask your question?
Thank you for the opportunity. I want to ask about the cryptography side from this scheme. For TRNG, you should test your random number with some standard tests like NIST at 122. And as long as I follow your presentation, I didn't see your test with NIST at 122. You just test it with NIST at 190 for entropy source. Because the quality of RNG is determined by its test, like NIC at 122, and you just show your entropy test for your scheme, and the good entropy is not a guarantee for the sequence to be random. And you can say that it's become random if you haven't tested with the standard test like NIST at 122. And how can you say random while you haven't tested yet? Thank you.
Yeah, I tested it. Yes, I tested it. I did not include the slides. I never include the slide with the results, because those are just a number that don't tell you much. And you should have them in the paper, but yeah, I don't see their usefulness in a presentation like that. But yes, I tested with SP822, and I have those results, and the random numbers pass all those tests. I tested 1,000 sequence of 1 megabyte. So I calculated, I don't know how you're familiar with SP822. So I calculated both the p-value of the p-values, so basically the p-value of chi-square test and the proportion of the past tests, and they pass. I have those numbers on the table, but I do not put them in the presentation.
And how many times you have test to get your p-value and proportion and all pass? Because the first time you try to test and the next time you get the data again, you cannot get the same result as before. And how many times you
so I performed so I did this
you test it.
Sorry. Maybe I interrupted you. Did you want to ask something more? Okay, so as I said, so I implemented, so I tested 1,000 sequences of 1 megabyte. So in total, that's 1 gigabyte of data. And that's the first time I tested it, it passed, and that's the results that I recorded. Indeed, as you said, if you test them again, you will get another numbers for that state.
All right. Thank you, Milos.